What? All right, hope that's better now. All right, the bold part will be part of the presentation. For the other parts, please have a look at the paper and the artifact. Similarly related work is part of the paper. I should probably provide a little bit background of what we are doing. So we are developing the Chrome browser, which is this huge piece of software. It's millions of lines of code. And realistically, the only real way to handle these kind of things, the complexity of such a project, is by splitting it up into components. So Chrome is split up into an actual browser, which is the UI shim and has all kinds of stuff embedded into it. It has a renderer component, which is kind of in charge of actually rendering a web page to your screen. And it also embeds a JavaScript virtual machine, which is called V8 for Chrome. There are many more. Those are the most interesting ones. And for this talk, I'm mainly talking about Blink and V8. And more specifically, we are interested in the boundary between those two components. But let's take a step back and look at the problem a bit more on an abstract level. The problem of cross-component memory management occurs when there is software that split into components with hard boundaries, like an API boundary in between that you cannot avoid. Also, what you need is a way to compose arbitrary object graphs across those components, and it requires that there is no static ownership of memory. So in this case, component A can own memory in component B and vice versa. And they can use potentially different managed environments. So to illustrate this a bit, assume that you're looking now at component A. It has no clue of what component B is doing, so it has to treat all incoming references as roots. There is just no information available, and the only way to deal with that is treating these references as roots. Similarly, you can play this game, same thing here with component B, and it should be no surprise that this will lead to reference cycles. And essentially, this pulls in all the existing literature on reference counting cycles and how you would break those things up. So what we are interested in, and I will get back to why this is relevant for Chrome, we are interested in providing effective, efficient, and safe garbage collection across those component boundaries. And why we think that is important is because we have seen V8 as a hands-on example being embedded in many different environments, and we have seen people getting it wrong all the time. So you have to be very careful, essentially, so that you don't create leaks or dangling pointers and are actually able to reclaim that memory. There is more related work in the paper. Browsers are really interesting in this context. So what did we decide to do? General approach for dealing with reference cycles is that you break up one of those links, right? So we did actually provide the system with the ability to reason about a different component. So in our example here, we could provide A with the ability to look into B and reason about liveness across components. And essentially, you want to have a look at objects that can transitively reach back into your component. For component B, though, we didn't do anything. It still will treat incoming references as roots. It's only required to break up one of those links. Note that in this example, we also have on the very top, we have a local object graphs. So in case of B here, it only sees the object graph of B. So A, though, sees the relevant objects of component B, which in this case is also the object that's part of the cycle. If you imagine, or we assume now, garbage collected environments, A can properly trace its own object graph. It can also trace, or cannot trace in this example, though, in the dead memory, right? So it can actually reclaim that one object, and it can clear those references. From B's point of view, now everything is okay, so it can now, on a garbage collection, reclaim its local object, and we are done, and essentially have reclaimed the cycle across the component boundary. Now, this is what on an abstract level happens. I want to now get back to what happens in Chrome. How is this related to the web, and what have we done in Chrome? So, and for that, the most important things are the document object model, which I will explain, and JavaScript as a language of the web to modify that one. There is lots of other stuff involved. It does not really matter for this problem, though. So the document object model is essentially cross-platform, language independent representation of HTML. It's well specified, and essentially it's encoded, or it's usually encoded by browsers in the object graph in the renderer. In our case, for Chrome, this means it's encoded as objects in Blink. JavaScript is the language of the web. Its uses are manifold, and there are probably way too many by now. It was initially intended to interact with the DOM and modify the DOM. You can essentially throw all kind of computing problems there. Feel free to do so. And we provide an environment where you can actually execute untrusted code. But the main focus initially was actually to modify the DOM. You can see an example on the right here. Very simple example. You just add an event listener to the document, and when the document is done, you execute that function, which just adds a diff element to the body. We'll get back to that just in a few slides, but that should be our minimal framing example here. How does this relate to this cross-component memory management problem? Well, we have now V8 and Blink. V8 has a custom object layout for JavaScript. This is essentially all the customized things that you need to make JavaScript a fast language on the web. It's also collected using a generational mark sweep compact collector, which is these days mostly concurrent and parallel with incremental fallbacks. For Blink, the DOM is implemented as regular C++ objects. They might use some fancy C++, but it's still the C++ object model. And in Blink, we actually have a very simple mark sweep collector that is doing incremental marking and sweeping, and some compaction on specific object types where it's simple. The implementation details, there are more implementation details in the paper, and feel free, I'm happy to answer questions, but it's not relevant for this talk, so I'm not going to talk any more about the actual implementations here. Because the important point is actually what we are dealing with is two components. They have vastly different memory layouts and objects models, JavaScript versus C++, and separate garbage collectors that actually are quite different these days. The one is relatively advanced, lots of concurrency, lots of advanced features. The other one is still very simple. And we kind of want to solve the problem of reclaiming memory across these boundaries. But in order to get there, we first need to know how the web actually works, at least in Chrome. And this is kind of the very basic. So objects are usually presented, the web page is represented in Blink as DOM. As soon as you reference something like the document from JavaScript, you get a pair of objects where one side lives in JavaScript, the other one lives in the DOM, in the C++ DOM. All JavaScript operations, you could use this object like an array, will happen on the JavaScript object. All DOM operations that are specified in the HTML spec are actually forwarded to the corresponding C++ object. And these two reference each other and essentially live and die together. Coming back to the very simple example we had before, I just want to provide an intuition of what's going on. The world, like the real world, is really complicated, but I think this should be enough to give a brief overview. This is vastly simplified. This is actually not really executing a whole lot of JavaScript. Like you notice that there are no references within JavaScript itself, but you already get quite a bunch of objects. And I think this should convey the feeling that you can arbitrarily compose object graphs and have these links across the boundary. There is also lots of stuff missing on the Blink side because the graph is actually better connected. So this was the real world. Let's get back to our toy examples. This is the simplified setup we want to have a look at. And essentially, we will use the V8 garbage collections to break cycles and allow V8 to see parts of Blink. So what did we initially come up with, or actually the people come up with a few years ago? This thing was called object grouping and was based on the observation. So it's still trying to break one link, but it's doing that in a specific way. It was based on the observation that JavaScript objects belong to a given DOM tree, and the DOM is mostly fully connected. So each node keeps the whole tree alive. What you can then do is an approximation. And objects essentially on the V8 side are alive as long as a single object in the corresponding DOM tree is alive, which is fine for objects A and B and their corresponding counterparts A prime and B prime, which is not fine if you look really closely. I said the DOM is mostly well connected, but there might also be nodes that are already disconnected, but still know which DOM tree they belong to through weak links or hidden links, which causes these weird scenarios where you have this node C that is kept alive because C prime is still part of the same DOM tree, even though it's not connected anymore, which causes memory leaks, actually. The situation for D is actually fine because everything is dead there. The properties of this implementation were that the implementation was relatively simple, and that's why the engineers went with this approach in the beginning. You only need this find DOM tree method for a given object, which will find you a group, and then you need to group these things and map back to V8. There are a few problems with that approach. It requires recomputing these groups after a mutator, in our case JavaScript, is executed again because JavaScript can modify the DOM and thus modify these groups. It also requires considering dead DOM trees, which is not nice for garbage collection because you want your operations to be bounded in live memory. So we didn't really like that approach and tried to find something different because this was definitely safe. It was not very effective. We still had memory leaks. It was not very efficient if you looked too closely. So what we came up with in the paper is this cross-component tracing, and the paper provides an abstract description of how you can pass around objects and references between multiple components. And the idea is essentially just to extend the tracing capabilities of V8 in this case to allow its tracing through Blink. It's very simple. It looks like just a regular object graph you would know, with the difference that it can work across hard API boundaries. The properties, the nice properties here are standard GC literature suddenly applies, and there is no custom magic needed. In fact, we implemented an incremental version of this, and for the experts in here, we just used a regular Dijkstra barrier without Dijkstra write barrier without actually checking the source object. So this was nice. We can just use regular literature. We did improve debuggability, which I will get to just in a few moments. Performance and memory results I will also show. The downside of this implementation, I think one has to be fair, is just that it requires quite some implementation effort because you suddenly need the capability to trace objects in your embedder. In this case, it's Blink for us. So we suddenly need object descriptors and layout descriptors that tell us how to trace these C++ objects, where are pointers, where are numbers, and so on and so forth. It also becomes tricky in the context of C++ and multiple inheritance. So you kind of buy into all this language magic on the embedder side. It is effective, efficient, and safe, though, which is what I wanna come to now with a few examples. But first, debuggability, because that was not part of the initial thing, and I realized that's the performance track here. We still care a lot about debuggability, though, and we care a lot about diagnosing memory leaks in JavaScript because they're very easy to produce, and in fact there is work in this area spanning multiple projects. There was a PLDI project that tried to, or that automated leak detection for JavaScript web pages, and we want to kind of help there by providing better retaining paths. So what is a retaining path? A retaining path is just a path along objects and edges that retains an object you're interested in. There is an example in the paper that just attaches one event listener that leaks a bunch of memory to the main body element. And for object, what you should also know is the objects in white here are part of JavaScript, and the other ones are part of, the gray ones are part of C++. So for object grouping, you obviously only had your entry points in a group, in a DOM tree, and your exit nodes. And this was the retaining path you got. And it was not very useful, to be honest, because it lacked all the information that was part of C++. With cross-component tracing, that naturally falls out because you just know all the objects and edges. In practice, this looks something like that. This is a screenshot of DevTools, which is kind of the debugger that comes with Chrome. On the left side, you see the last version that implemented object grouping, was release M57. And I think you can already see that there was only a vague concept of a document there, and this was essentially a group. On the right side, I mean, there were lots of improvements happening, but I think the main story should still be clear that essentially you can trace along all those nodes and edges to find your memory leak. So this is kind of the debuggability side of the things. The rest of the experimental evaluation, we used Chrome M57. That was the last version that essentially implemented both versions of this memory management system. We used Chrome's Catapult Performance Benchmarking Framework to benchmark on real websites. This is a record and replay approach where you can actually record web page interactions and replay them without going through the network stack and a few other things. So you can make it actually somewhat predictable. We benchmarked multiple configurations. Only two of those are interesting here, though, which is a baseline, which is incremental marking with incremental object grouping. So we did object grouping in incremental steps, very well realizing that we have to throw away these groups, but we still could make progress on the transitive closure, so that was a win. And we compare it to incremental marking with cross-component tracing. The metrics we use are for throughput, total garbage collection time in V8. For latency, we use the time for the main finalization pause and mutator utilization. We also sample memory. We record 10 runs per web page per configuration and compare using Wilcoxon rank sum test because we cannot assume a normal distribution of these results. And we showed a 95% confidence interval. So how does this look like? The graph on the right, like there are many graphs like this in the paper, essentially is for the finalization pause where we compare cross-component, the incremental version of cross-component tracing against the baseline. On the x-axis, you see the web pages, and on the y-axis, you see the comparison against baseline using the estimated result of the rank sum test. We say that the result is significant if its 95% confidence interval does not include the 1.0 value, which would mean that they are equal. With that, we actually improved six of these benchmarks. We regressed 2, and 8 were not significant. After submitting the paper and the final versions, we digged into why this was happening, and it turns out we actually did fix the scheduling for GC to make it more predictable, and this had negative side effects on the new implementation. So we since then have fixed this kind of issues, but this is kind of the snapshot you get in the paper. The rest of the results, for throughput, we did not observe significant changes back then, which meant that essentially the write barriers and incremental approach kind of evened out with the grouping we had. We did observe improvements on mutator utilization, which is a metric that compares for a given time window how much time is spent in GC versus time spent in mutator. We did improve it in single-digit percentages across the board. That's kind of expected because the main GC pause still dominates, so there is not much more to gain with just improving this part of the GC. For memory, we didn't observe significant changes on the benchmarks, which is also expected because the average case behavior for object grouping is kind of okay. We realized, though, that the bug reports for the leaks stopped coming in, so we kind of fixed those leaks in the wild, which is nice. The takeaways are that cross-component tracing improves over object grouping by reducing leaks, improving latency, and improving debuggability. But there is one thing I wanted to still highlight. I'm always talking about efficiency here, and I think it's kind of relative. And there are a few observations when you look at this work, which is kind of our future work right now. We currently need the V8 garbage collector to break cycles, which means that you should be very careful when scheduling garbage collections. And essentially, scheduling 2 GCs is a nightmare. It's a bag of heuristics that you always get wrong. And you always have to trace through the set of live objects twice, which is also bad, which is why we are unifying this approach in doing one garbage collection across both heaps, essentially. And with that, I'm happy to take questions. Are there any questions in the room? Let's check the slide real quick. Any questions? There is a question. Perfect. Sebastian, could you please sit up?
thanks for the talk. Can you hear me? Okay.
I will repeat.
I think this is a generally useful technique, especially if the components are separated by process barriers or machines. In your case, that seems not to be the case, though. Have you considered trying to unify the two heaps? Obviously, they have different constraints, but that would be feels like the ideal solution.
So I guess the question is, have we tried unifying the heaps in general and merging kind of the components here, right? There was actually a project that tried to essentially represent the DOM in JavaScript. It was done a few years ago, and it came to the conclusion that back then, at least, JavaScript was not ready as a language to represent these kind of things that you need from a DOM. Also, what we lacked back then is fast access through the API, because we still will keep an API boundary for V8 because it's embedded in lots of other products. So we essentially lacked a mechanism for fast access to the DOM, which the layouting and the Paint API essentially need.
So there are questions on Slido. Shocking. I'll read it using the mic so that people that are listening.
But I actually probably didn't answer. So we have tried but failed to do so. That's why we stick with this one.
Sorry, I interrupted. So one question from Slido is, how complicated is it to implement cross-component garbage collection for two managed heaps?
For two managed heaps, I would say it's actually doable. The problem would be if one of the heaps did not actually provide a tracing mechanism, because then you essentially need to build a GC from scratch. We were relatively lucky, though, because we essentially could build on two managed environments, so the tracing mechanisms were there. So it's essentially about hooking those up. So I think if they're there, then that's definitely doable.
Okay. I think that we're kind of running out of time, so I apologize to that person that asked another question on Slido, but we have to move on. Thanks. Let's thank Michael again. And next talk will be